Okay, so challenge problem number 11 is an interesting problem. The first part asks us to derive an expression for the peak voltage across the capacitor in an RC circuit. So I outlined the problem right here in this little, just a really small diagram. It's really simple. But to find the peak voltage across the capacitor, eventually I said the peak voltage is just equal to E, which is kind of, is equal to VC, but I said EMF C, which is just the voltage across the capacitor. First, we have to find IT. I call it IT for some reason, but it's basically the current right here across the capacitor, and to do that, you have to find Z, which is the impedance, and because this is an LRC circuit, it's just an RC circuit. It just has a resistor and a capacitor. So you just have to worry about the resistance and the capacitor reactance, which is just XC. So you don't have this, and this is a plus. I already even wrote down plus sign instead of minus because this is squared, so the minus doesn't matter. But there's also not an epsilon here because there's no inductor. It's just an RC circuit. Anyway, so you find Z, you plug Z into where this goes, which is Z, and then you know that XC is just equal to 1 over omega C, so you can plug that in there. Once you have I, we know from the book that VC, which is the voltage across the capacitor, is just equal to IC times the capacitive reactance. So you can just say VC is just equal to E naught over the square root R squared plus 1 over omega C squared times 1 over omega C. And then I just rewrote that right here. It's basically saying the same thing. I just took this fraction and brought it in. So it's one quotient. So this is a pretty valid expression for the peak voltage across the capacitor in the circuit. However, this is definitely a frequency dependent thing, because when VR is equal to VC, which is what I wrote right here, and omega will then equal omega C, you have a crossover frequency. So that basically means that omega C will be equal to, this is what's said in the book, that omega C will be equal to 1 over RC. So that's actually really, and then you can rewrite it as RC equals 1 over omega, which is really nice because that will allow us to get rid of these R and C values. So if that is the case, and the rest of this down here is just basically just there in the case that that VR does equal VC and omega does equal omega C, and the source is outputting crossover frequency, which means that that you can basically just bring on the C under the radical, and you have to square it. So you bring in C here and here, square it here, and then also square there. And RC is just equal to 1 over omega. So you have 1 over omega plus these cancel, 1 over omega squared, and then you get this, which just cancels to EC equals E naught, which is the peak voltage across the capacitor is equal to E naught source voltage divided by root 2. So that's extremely simple. That's a really nice expression, but it is only valid in the case that the circuit is in the crossover frequency, or that omega C is equal to 1 over RC. Yeah. So if it wasn't that, if the frequency was something different, this wouldn't be right. But we could just plug in constant values for C or R, which we don't have, so I didn't do that. Okay, part 2. So part 2 is really simple because I just use the really simplified expression in the case that the crossover in the case that VR equaled VC. So E for low frequency, which is just the voltage across the capacitor for the low frequency. The low frequency was 1 radian per second, which is really not fast because that's 1 revolution every 2 seconds, which is really slow. But that's just 10 volts divided by root 2, which is just 10 over root 2 volts. And then for voltage across the capacitor of a high frequency, it's 1 volt over root 2, so it's 1 over root 2 volts. So that's really easy. Again, that's only, okay, so I talked about the other case down here, but again, that's only if omega c is equal to 1 over RC. So if omega wasn't equal to omega c, then if it wasn't functioning at crossover frequency, then you'd still have to use this expression. And it would be possible, I suppose, to get a numerical value for the voltage across the capacitor at low frequency and high frequency if you use this expression and omega was really high or really low or something like that. If you plugged in numbers for C and R. I didn't do that. I just used this, but that's definitely possible. I don't think the problem gave us C or R, so I just stuck with with these guys for the third part. But that's definitely a possibility, is to plug in numbers for C and R. So for part 3, basically asks us to plot the source voltage versus time, and then plot the capacitor voltage versus time. So this is the voltage across the capacitor, and I guess it doesn't get any bigger than that, and then the voltage across the source. So you can see these are really two similar curves. The only difference, and this is exactly what you'd expect, the difference is the fact that the amplitude changes by 1 being over square root of 2, and the square root of 2 is something like 1.41 something. So it's going to be a little bit smaller. So voltage across the capacitor is, you can see that the amplitude is a little smaller. It's like between 6 and 8, so 7 as opposed to 10, and that's what we would expect. I think this is a picture where it's a little more spread out, so you can see it better. So again, this is the voltage from the source because the y-intercept is about 10, which means it's not divided by root 2. But again, it's just a sine, well, it's cosine, basically a cosine wave, but with a cosine in there as well. So another part of the third part asks, well, what's an application for this? And this type of wave is used all the time to do things like data transfer, things for the internet, and things for television. Like, it's a lot easier to send one wave that's also carrying another smaller wave in it, so that data can be transferred more fluidly. And I also read, just because I was reading the book on this section, part of the book that talked about filter RC circuits, and the two-part equation that you can use to make these two kind of sinusoidal waves can, I think, maybe act as a kind of a filter to filter out the noise and make the curve more, just kind of smooth it out and make it better, which would, again, any frequency filter would be advantageous in any kind of data transfer, or something for the internet or television, or I guess not radio, because radio just uses radio waves, but anything like the internet or something like that. Okay, so I hope that was a good explanation.